So hi everyone, my name is Avihu. I'm head of product at Starkware, and together with Shahar, we're going to talk about recursion, Stark recursion using Cairo. As I said 2 minutes ago, I'm going to go over a specific implementation that we are using in Starkware. And this will be like the first 25 to 30 minutes. It will be a high level description of this recursion. And then Shahar is going to probably go more into the details. Shahar, maybe you want to just introduce yourself and then I'll go.
Sure. Hi, I'm Shahar. I work with Avihu. I worked on the Stark Recursion in Starkware until very recently. So I have a lot of more knowledge about the details because I wrote some of them.
Okay, great. So let's start. So today I'm going to cover a little bit of background that is needed. I think I would assume that some people in the audience has the necessary background, but anyway, I'm going to cover it. I'm going to explain what is recursion and what is recursion when it comes to proofs. And then I'm going to talk about some great benefits that recursion brings with it. And at the end, I'm going to mention some numbers and some optimizations that we applied to it on in Starkware. Okay, so first I wanted to say that this is like the third time I'm giving this talk, and I'm always playing with the idea that once I have enough talks, I would just get to this point in the presentation and click on start on the video, and then it will up to this point, and then at this point of the video, I will click on another video, and it will play then, and that all the way down until the end of the talks. But I don't have yet enough talks to do that, so I want this will be probably the only stupid recursion joke that you will see in the talk. And now going straight to the background. So here are the things that you should be familiar with in order to go through the presentation. So one topic is proofs and Starks. I'm not going to get into it almost at all, except explaining the basic idea, which I'm pretty sure that most of you are familiar with. I'm going to mention what Cairo is. I'm going to talk a little bit about Sharp, which is a shared prover. And I'm actually not going to talk about Starknet, but some of the things that I will mention are related. And if you don't know what Starknet is, you're welcome to ask afterwards or to talk with us later. Okay, so the basic principle that we are working with is that suppose that we have a computation that runs in times t, then what Stark proofs and Cairo gives us is that we can generate a proof to this computation in times that is proportional to t. For simplicity, I will just relate to it as t as well. And the verifier takes only logarithmic time in t to verify the correctness of the computation once it can check the proof. And what Cairo is basically a language that was developed by Shahar and others in Starkware that supports taking any logic, basically write it in Cairo, and then it's straightforward to prove it. So it's a language that enables you to express your statements, the logic that you want to prove in a software language, and then easily be proven instead of like complex polynomials. So the basic idea obviously is, let's say you have some program that you want to generate proofs of its validity for a given input. So you take your program, you write it in Cairo, and then the prover side runs the program, the Cairo program on some input X, and you want to show that to the verifier that this program generate outputs Y. So it provides a proof to the verifier, and the verifier is going to verify this proof. And once he did, and everything is okay, he is now convinced that the prover knows the right output to provide to give sorry, it knows the right input to provide this output Y on this specific Cairo program. Great, so now we went over proofs and we went over Cairo, and now I can explain a little bit what SHARP is. So SHARP stands for shared prover, and basically what SHARP knows to do is to take different Cairo programs with different inputs and prove all of them in a single proof. So for example, let's say that we have a Cairo program that is StarkX in some version. Here I put the version that runs on immutable X. A different StarkX program, a different Cairo program that runs on a different system, Shahar, and a third Cairo program that is StarkNet. And each system here that has a specific Cairo program can have the inputs for the program to be a different set of transactions, obviously. And every job in this slide means, a job means basically a Cairo program and the list of transactions as the input for it. And what SHARP knows to do is to receive different jobs, different Cairo programs with different transactions as input, and combine them together to a single proof that he sends to a verifier on chain, and the verifier knows to take this single proof, verify it, and basically register that all those programs had some statements correct in case that the proof is valid. Okay, so now that we have all the background, we can dive into recursion. I assume that most of the people in the audience know what recursion is, but I think in the context of proofs, it's easiest for me to explain it with this analogy from a TV show called Rick and Morty. I actually watched this specific episode a few days ago. So what's happening in this episode is that there is Rick, he's like this crazy scientist, and he has a spaceship, and the spaceship engine got broken. And turns out that Rick basically had an entire universe he created that generates electricity to run his spaceship. So he goes into this universe and he finds out that this universe created a different universe to provide them the electricity. And together with other scientists, they jump to the third universe just to find out that this universe also is working on another universe to generate electricity. You understand where it goes. Okay, so what is recursion when it comes to proofs? So what we are used to talk about is that normally we have some original program that we all want to generate a proof and verify it on a verifier program, and this is what we do. We prove the program execution and we send this proof to the verifier, and everyone are happy. But the thing is that this verifier program is a program by itself. So instead of proving the original program, we can also prove the verifier program execution. And once we do that, we can verify the verification of the proof in a second verifier. And it can go on and on. We don't have to stop there. We can also prove the verification of the verification and go deeper and deeper in the recursion. It's okay, it all sounds very nice, but what is the motivation? So to explain the motivation, remember that if we have two programs and we have generated a proof for them, then exactly like we can in SHARP take two programs and generate a single proof for them, we can also take two programs that are verifier program and generate a single proof to two verifier programs at the same time. And also that it's true that the original program takes, if it takes T steps to run, it also will take roughly T steps to prove, but running the verification of the program or running the verifier program only takes around log square steps to run, and therefore, according to our simple logic, log square step to prove. And we can use that. And here is like a hint of how we can use that. So let's talk about the benefits and why do we want recursion. So one clear benefit is that we can reduce the amortized gas cost per transaction and increase the proof capacity. How do we do that with recursion? So until now, or up to this point in time, we in Starkware, when we generate proofs, we are limited. We are limited because say that the strongest machine we could find on anywhere can handle T steps of some program. It can prove T steps in the largest possible setup. Then this means that if, let's say that every step is a transaction, we could the maximum that we could prove is T transactions. So that means that if the verification costs yay millions of gas, and remember that the verification doesn't go, it goes very, very slowly with the cost, then it basically means that the amortized cost per transaction is bounded by some number. But what we would like to do is we would like potentially take several machines and still have at the end of the process a single proof. And this is exactly what recursion enables us to do in a very straightforward way. So take a look at this diagram. You have, let's suppose that this larger box is the machine that generated proofs and it has capacity T. So far we could only push inside this machine a prover that can prove T steps, and that means one program. But what if we had two programs, we had to generate two separate proofs to be verified. Oops. And what we can do using recursion is to say, okay, let's prove every program separately, but let's not finish here. Instead, let's wait until the second step, and then since most of the times log square T or 2 times log square T is much smaller than T steps, then we can still take those two verified programs and prove them together and basically send a proof for the verification of those programs to the chain. And in this way, we increased our capacity 2x, but we don't have to end there, obviously. We can do it also with 4 programs and in some, in a tree structure. That means that now those 4 programs, even that previously they would require 4 separate proofs, they now, at the end of the day, we only send a single proof to the on-chain verifier for 4 times more steps. And that means 4 times more transactions, and that means 4 times lower cost. And it can go on and on. It can do a lot of savings. And another great benefit is latency. And by latency, I mean the time that programs or user wait before their transactions or proofs for transactions appears on chain. So if you remember previously when I explained about Sharp, there were like 3 different programs, and they sent their jobs, to Sharp to be proven. Every job was like a list of transactions with their own program. And what normally happens is that those jobs, they're not arriving necessarily at the same time. They arrive sequentially over some time based on the speed of transactions. So you normally wait twice, or up to this point in time, you wait twice in Sharp. One time because Sharp is waiting until enough transactions has arrived or enough time has elapsed before even starting to generate the proof. And then only when this time has elapsed or the number of transactions that arrived, then it starts to generate the proof, and then you still need to wait the entire time of the proof generation, and it only happens on a single machine every time. So it's fairly slow. And what we can do with recursion is that we can improve those 2 aspects. So with recursion, the first advantage is that we don't have to wait. We can start generating proofs to a job that has arrived without waiting for the other jobs to arrive, still knowing that at the end we could unite it to a single proof. So we could take this job and generate a recursive proof for it without waiting for the second job to arrive. And the second advantage is that even if those jobs arrive at the same time, we can work on proofs in parallel on different computers. And eventually, the effect of it is that when we decide that the time has arrived and we should release the proof, we don't have to start generating the proof. We are most likely at a position where we already have almost everything proven, and we maybe have to unite the last branches at a tree and create a single proof which will go on chain. So that saves basically twice. One time for waiting for transactions before start proving, and the other time is that you can prove things in parallel on different computers. Okay, so we spoke about gas cost and proof capacity, and we spoke about latency. I want to mention a few more concepts. So one concept that we very much like is the one of layer 3. So I didn't explain on StarkNet almost at all, but for those who are familiar, StarkNet is a layer 2 operates over Ethereum. And what it means is that it's an environment where people can send transactions, and once in a while, these transactions are being proven, sent to Ethereum, Ethereum verify the transaction, the state transition, and if it's valid, then relates to the new state. But we don't really, once we have recursion and we have a Cairo program that knows to take proofs and verify them, we don't have to stop there. And we can go deeper into the layers, and we can generate a duplication of StarkNet as layer 3, or even go deeper in the tree. And this meme is just to give you the idea of what can be done. It also goes in the opposite direction of what you're used to. The base layer is at the top, and then the layers on top of it is actually going to the bottom, but that's how I see the world. Anyway, here's how most of the people see the world. So normally what we have is we operate normally with a solidity verifier on Ethereum, and we send proofs to it. But what we can also do is we can deploy this Cairo verifier that we already have from the recursion. And then you can imagine that there are many, many different systems. Some of them are just replications of StarkNet that can operate on layer 3. Some of them are different Cairo programs like StarkX, and others can be whatever Cairo program that you have in mind that for some reason creates this environment that you're very interested in. Some people are interested in creating an environment that mimics the EVM. Some people are interested in a different execution environment, for example, the Orbit VM. So whatever environment you're interested in, you can implement it in Cairo and send it to the Cairo verifier to be proven. And the advantage of doing this and not doing it directly with the Solidity verifier is, first of all, the cost. And second, that once you have those different environments, communication between those environments through StarkNet is much cheaper and probably feasible in terms of costs. Okay, what other benefits recursion brings? So I will talk, I think there are a few more, but I will only touch one last important improvement. So up until now, or maybe I should step back for a second. The way Cairo works, Cairo itself is a simple VM, but from time to time, we do need, for example, some cryptographic primitives to be specified explicitly in equations in their error form and not written in Cairo. And the reason for this is we want greater efficiency in proving them. So those primitives, when they are expressed in error form and combined into Cairo, we call them built-ins. And it helps us. So for example, if you want a hash function that is like very efficient to prove, we add it as a built-in to Cairo, and then we can use this built-in in Cairo programs, and this built-in will be proven more efficient. But that most of the time means that every built-in that we add, we need to also add supports in the verifier. At least when it comes to Starks, the verifier should be aware of the new error that was added, and that means that it will require a special layout. And in turn, that means more layouts, but it also means that the solidity verifier become more complex. And more complex means more gas, and more gas is not something that we want. So if we would just operate in this model, the more built-ins we will add, the more complexity we will add to the solidity verifier, and we don't want that. But with recursion, we can now avoid it, because with recursion, the solidity verifier is good enough with just knowing the built-ins that required to verify the last recursion step, this step. So everything that he needs to know, he will know, but everything that all other built-ins that are not being used in this recursion step can be incorporated only in layouts being used by verifiers in Cairo and never reach the solidity layer. And that means that adding more built-ins now doesn't add complexity, at least to the solidity verifier, and it also doesn't add gas cost to the verification process, which is great and probably will enable us to add easily more built-ins without increasing the gas cost. So one example that hopefully will come very soon is the Ketchup built-in, which is a very complex built-in, and adding it to the solidity verifier will probably cost us not something that is negligible, but adding it through the recursion will probably make it will remove the need to make the verifier expensive. Okay, I have 4 minutes. I want to mention some numbers and maybe get to one optimization. I don't think I will have more time than that. So this is not a theoretical construction, but rather we're probably going to production next week. Sorry, not next week, the week after next week, the second week of August. And this is only a first version, so there are many things that we know that we can improve there. But even on this version, to the specific time windows that we set and the length of recursion step that we have, we still, on a conservative estimation, we will still gain 8x more transactions in a single proof, and we'll be able to, at the best case, improve the latency by a factor of 4x. So that's already impressive, and that's before any optimization. So what I'll just go over the optimization fairly fast. Maybe I'll just talk about the first optimization, and then Shahar, if you want, you can also mention the later ones. Okay, so I want to talk about flexible hash commitment. So what is flexible hash commitment? First of all, let me introduce you to, I assume that most of the people you are familiar with, but in case you are not, we are using currently 2 hash functions in our construction. One is Pedersen. The guy here, I think, is Mr. Pedersen. It wasn't that straightforward to get out his picture of the internet. And Pedersen is a hash function that has an algebraic structure. Therefore, it's very efficient to prove, but it happened that it's pretty slow to compute. And on the other hand, there is Blake, which you are probably familiar with. It is very fast to compute, but doesn't have a simple structure, and therefore not so efficient to prove. And the way that it works today is that inside the prover, when we build a commitment tree, and if you don't know exactly how the prover works or how Stark works, so just treat it as a black box that needs at some point in its execution to basically take a very long list of elements and create a Merkle tree commitment on top of them. And today, to generate this Merkle tree commitment, we use the Blake hash function. And I'm going to try to convince you that this construction on the right will be more efficient. So basically, in simpler words, we have this and we want this, and I'm going to explain why. So what do we get? Let's start with a verifier program. So the verifier, what it does is basically it doesn't treat the entire commitment tree. It only takes a single path of the tree, and he has to verify them. And the fact that the verifier has to verify them means that the Cairo verifier program we will need, in the Cairo verify program, we will need to prove the verification of those numerical paths. And because of that, if we look at one path, and before this path was made of Blake completely, and now we replace some of this with Pedersen, then the verifier work will become smaller. And this is even, I just want to say one more thing about that. What you see here is if, for example, we take, let's say that the depth of this tree is 32 layers, and we take 22 and make them Pedersen and not Blake, then you'd say, okay, then we get 3x improvement on the efficiency of the verifier. But the fact is that this is an improvement of more than 3x, because the verifier checks trees, not just this tree, but it checks trees that are going and getting smaller and smaller from the upper layers. So that means that in fact, the verifier will have even less work than 3 times x. It will get, theoretically, I would say that it goes like square divided by 2, like arithmetic series, but it's not that accurate because there are also jumps. Anyway, I don't want to get into it, but just keep in mind that the verifier program becomes much more efficient. But now you will say, okay, but the prover now pays much more because look, you took 22 out of 32 layers and you made them slow to compute. Well, this triangle is pretty misleading because when you imagine this, every layer of the tree has twice the number of elements than the previous layer. So in fact, this triangle should be look more like this and actually much more to the extreme. This is my drawing skills. So an example with numbers, for the prover, let's say that we have 32 layers. So previously the prover did pretty fast computation using Blake, and now we switch 22 layers to be Pedersen, so it's slower to compute. Let's say that computing Pedersen is 1,000 times slower than Blake. We still replaced only 1 out of 1,000 hashes at the tree. So we only made a commitment cost 2x more to compute. And if we remember that commitment is not the entire work of the prover, but let's say 20% of the work, so the total overhead will be something like 1.2 over the existing prover. So overall, the prover pays 20% more, but the verifier earns maybe 8 times faster. So overall, we get an improvement that is close to 8 times. Okay, I won't get into this because I want to leave time for Shahar. So first, just to say what we've seen so far. Recursion is great. It helps us boosting performance in terms of amortized gas cost, capacity of proofs, latency of generating proofs for transactions. It helps creating layer 3s with a recursive verifier or the Cairo verifier. It enables us to add built-in faster and with less complexity. It goes into production in 2 weeks' time. And there are many more optimizations that we know of and that we're ready to apply when moving forward. That's my part. Thank you very much. You now get to hear Shahar, which, well, basically he implemented most of it. So that's the point where you actually see, I hope, maybe some code or can ask some more low-level questions.
So Avihu, what's the depth of the recursion and when this is deployed? What do you think the maximum depth of the recursion is going to be?
It really depends on the time window and okay, 3 things. It depends on, first of all, how much time are we ready to wait? Second, what is the time of a single recursive step? And third, the load of the system, because it's not like a theoretical system, it's a system that runs in production. So most of the time, unless there is a very heavy load, it won't get more than, let's say, 20 or 30 jobs in its lifetime. So what we are currently targeting is depths of, I think the deepest we can go now, or we target to go is 8, but I think it will very rarely happen. I think most of the time you'd go 5 times. Sorry, the deepest is 6 actually, not 8. 6, and I think you won't go deeper than 5 in practice.
Mhm. Yeah, I see. And the verifier itself,
Go ahead.
I guess maybe Shahar will talk about that, but the verifier itself is now written in Cairo. That's
Yeah.
that's what enables recursion to happen.
Yeah, and the fact that it's written in Cairo is probably made it easier to write it, and also it's more flexible. So, for example, if you want to do things like this, and tomorrow somebody comes and say, "Hey, I have a different hash function. I want you to check, or we want to replace it," then probably implementing it in Cairo or implementing the flexibility of choosing how many layers in Cairo is a much easier way than using expressing all this in air. Okay.
Yeah, thanks.
Thank you. So Shahar.
Hi there. It's my turn, I guess. Great. Well, first of all, I'll try not to repeat things that Avihu said, but I did say a lot of things, and some of them I wanted to say. Also, I'll give some low-level details. If you want to ask questions, please do. I have time for questions. And can I share my screen? I'll share my screen. 1 second.
You should be able to.
Yeah. Okay. This is my screen. I prepared some things here. Yeah, and later, maybe if we don't have a lot of questions and we have time, then I'll show you some of the code, which is nice. So we want to do a recursion for a lot of reasons, but how do we do recursion? Basically, we just need to prove a verification of Stark. There are some other approaches out there that people already implemented. Some involve just writing a verification logic in polynomials, which is hard, maybe not that efficient sometimes, because you do some computations multiple times because you need that polynomial structure a lot of times. You can do it in circuits. That is also done. But we are doing it in Cairo. Why? Because we have Cairo. It's general computation. It's pretty easy to write it, and it's pretty efficient as well. So basically, it means writing a Stark verifier in this language that is called Cairo, that we have tools to verify. You can think about it. One approach would have been to just take our existing verifier. We have verifier in C, verifier in Solidity, maybe try to compile it or copy it into Cairo in some ways, but they would be not that efficient. And one of the major requirements, I think, that for everything we do is efficiency. Cairo is designed for efficiency. It uses only 50 less variables per step. We use very efficient provers. So we want to be as efficient as possible. So we chose to write it in Cairo. So what's up with Cairo? Just a bit, some properties that will maybe affect our verifier, sorry. Well, the basic data type in Cairo is a field element, which is good for us if this is the same field that we want to verify the proof at, which we do. We only restrict ourselves to verification of Cairo proofs, not just any star proof. So again, we write a Cairo verifier in Cairo, and that means that the field that the proof we verify works on is the same as the field that Cairo works on. So we have a basic data type of field, which makes all the field computations very efficient. Now, like Avihu said, hashes that are cheap for Cairo are expensive for regular machines, for x86, for the prover essentially, and vice versa. The examples we take usually are like Pedersen and Blake. Pedersen is cheap for Cairo and expensive for x86. Blake is cheap for x86 and expensive for Cairo. So
Avihu, why do you not use Poseidon, which would be good for both?
Yeah, I mean, it's a good question. Why? First of all, when we started working on things on Cairo, Poseidon wasn't that established. I mean, it was established as part of a competition we started. So we already have this big infrastructure that makes Pedersen work very well in Cairo. We don't have Poseidon. Poseidon is it's good for both, but I'll claim later that it doesn't really matter. Like it's enough to have something good for this and good for this.
Okay.
All right. So yeah.
But just to add to it, it's very feasible that for other reasons you will also see Poseidon not so much far into the future as a built-in as well.
Yeah, that's true. All right. Yeah, Cairo is Turing complete, which is good. We can write a lot of stuff in it. A lot of other ZK infrastructures are not, which makes it harder to do like unbounded loops, like loops that you don't know how many steps it'll take. We can do recursion. We can do a lot of neat stuff. Cairo is using somewhat different architecture than regular languages. It has an immutable memory and some non-determinism, which makes it less translatable from other implementations of the verifier. And Cairo has a high-level language that we can write our verifier in, which is great. So these are the properties of Cairo. Now, what does historic verifier have? One basic building block is a channel, is like the fiat Shamir reduction. Basically, the proof protocol has an interaction between the prover and verifier, and we simulate this using hashes. So basically, when the prover sends something over the channel, we just hash it, and this gives us the random bits of the verifier. So this channel has hashes, not a lot, so it doesn't really matter, but we use some combination of Blakes and Pedersens there for when it's easy to do that or the other, but they're not a whole ton, so it doesn't really matter. Other things we need to do is evaluate polynomials. Again, it's in the base field of the Cairo, which is very nice and it's very efficient. Verifying a fry. This is the low degree testing, also mainly field operations. And the major work here, the heavy lifting, is verifying Merkle authentications, which is for the verify side, the log squared hashes, which I'll get into it in a bit. It's like the first optimization is like Avihu said. The question is which hash we're using for the Merkle authentications, and the prover needs to perform n hashes, while the verifier needs to only do log squared. So it makes sense to optimize for the prover, but we can do better. We can make some of the layers in this hash and the other in other hashes. So the basic thing scheme here is Pedersen is about 1,000 times more expensive on the prover side, which means that if you take this Merkle tree and just a basic recap about Merkle tree, we have 2 to the k leaves, and each interior node is a hash of its 2 children, and so we can do that. The bottom 10 layers are using Peterson, which is verifier friendly. I'm sorry, the top 10 are Blake, because the prover needs to do a lot of these operations on these layers, like this is 2 to the k, to k minus 1, etc. And only on the top layers, he will do hashes that are cheap for the verifier and expensive for him. There is this asymmetry between how many hashes the prover needs to do and how many the verifier. Well, this makes it look like, okay, so the prover pays about the same, but how much do we gain for the verifier? The verifier, for each authentication path from the root to the leaf, he has a 10 expensive ones, and the other one are not as expensive. So if the height is like 30, it sounds like it's he only does 30% of the work, but it's actually a lot better than 30%. It's more like 10%, or even one could claim it's a constant in a way. If you dig deeper into Fry, there are multiple trees. You know, we have a big tree of height log n, small tree of height log n minus 1, log n minus 2, log n minus 3, and so on. That is where the log square comes from. The verifier needs to do a verification path on the big tree, on the small tree, and this sum is a log squared. And when we choose which of these hashes to perform in Blake or Peterson, in the verifier or proof friendly, and a simple analysis is just to look at how much each layer saves or costs for each one. Well, if we look at this big layer of 8 nodes in this case, then the verifier needs to only do 1 hash on this layer, this X verification. The prover needs to do 8 hashes. So if I convert these hashes to prover friendly, we gain a lot. The prover gains like 8 good hashes, while the verifier only needs 1. If you do it on this layer, it's a bit, the ratio is a bit worse. It's like only 4. So these are the second layers we would take. These are the third. And overall, the 10 layers would only be on the first tree. The second tree will have 9 layers. The other tree will have 8 layers, and so on. So basically, we just have about 55 layers for the verifier that it needs to make out of this log squared of n. Just 50. So it's more like 30% squared, the amount we save here. So this is just a bit more details about this optimization. Another optimization we can do is regarding the blow-up factor. So what is the blow-up factor? Part of the Stark algorithm is, like you've seen him above, committing using a Merkle tree on a low degree extension of this data, of this trace. So what is this degree of extension? It's a parameter, we can play with it. When we take a bigger degree of extension, the number of leaves get bigger, and the prover needs to do more work on in the interpolation and computing the hashes. The verifier, though, needs to do less work because each query gives him more certainty that the proof is correct. So it needs to do less queries overall. So this is like a trade-off. And usually without recursion, we chose it to be maybe 16, let's say, which is not that small. Because we wanted the verifier to be cheap. Stark proofs are already not as small as the comparators that they're Snark. They're like about 70 or 100K, and the verification, for example, today on Ethereum is almost like a block. So we want to save on the verifier. It's very important. But now that we have a recursion, we don't really mind because the verifier is not actually running on Ethereum on the actual verifier. We will have a recursive proof on this verifier. So if we think about the tree of recursion, that every node is like is a proof, and we have 2-to-1 compression proofs, then all of these proofs, except maybe for the root of the tree, can be very expensive in a way because they are proved. They're still off-chain. They're still no one will actually verify them except the recursive prover. So basically, we save a lot of prover work on all the jobs except the last one that does the last recursion step. We make the prover cheaper and the verification more expensive. If I give an example, if we look at this as the recursion tree, then think of it, we make every proof, let's say 1/4, fourth of the time of the proof. But this in turn makes the verifier cost 2 times more. But we do the same thing here. We make the proving of this layer cheaper, and this costs 2 times more for the proving. And then we can do this same here. The proving okay, here we don't do this this thing because we want the verification to be very cheap here too. So yeah, so overall we save on the proving time on almost all the node while still making the proof at the end not bigger, or almost not bigger.
So what's the degree extension that you end up using in the recursion?
Well, we are experimenting right now with all kinds of things. So instead of 16, we think about maybe going 4 or 2, but really depends on the layout and the exact built-ins we have, because there are some aspects of the prover itself that are not scaled by the blow-up factor. That means that lowering the blow-up factor doesn't save time on these steps, which is like computing, evaluating the composition polynomial, a lot of points, and also kind of other stuff. So yeah, it's some say fine-tuning of parameters over there. It depends on the job itself. All right. Well, about soundness of recursion, basically it's a lot of words to say that we don't know. We don't know really how to analyze these recursive proofs. The main issue is the soundness analysis we know today about Stark proofs. Assume real interaction between prover and verifier, and we use the fiat Shamir. So when we just use it once, we say, "Oh, okay, I can believe it." We proved it for regular interaction, but fiat Shamir looks safe. But when we start to do recursion, then we don't really know how to analyze this proving of verification using fiat Shamir and not a real interaction. So I'd say you're just missing some tools to analyze it. If you have ideas to how to make formal analysis of this recursion thing, be great.
I just mentioned here that there are some, I think, 2 works. One is like closer to be finished that are being done by like partially people from Starkware, and I think there are some directions. So if it's relevant for anyone, we can introduce afterwards.
Okay. Maybe Avihu touched on it. Some of the benefits we have from recursion is a parallelization. If we have this big proof, a lot of the steps of the proof are parallelizable, but they share the same memory, and we need a machine with really big memory to make this large proof. So instead, what we can do now is split it into small proofs, and each one runs on a machine with a lot less memory, which are a lot cheaper, and overall gain a lot of benefit. Obviously, reduced latency. And write this right here, but yeah, we can have a reduced latency by scaling a whole lot on this parallelization. Total proof size verification cost, obviously, because we compress a ton of jobs into something that looks like a verification of a single job. So yeah, another neat thing we can do is public input compression. I'll give a small example. Today on StarkNet, the public input we output is basically the state difference for each storage cell that the program touched. We show the previous value and the latest value. So this thing costs data on chain. But when we take two such state changes, two proofs, we get a smaller state diff because there are cells that were changed by both of these proofs. So if because we were bounded by the maximum size of the proof, we could only take, let's say, 1,000 transactions and output the state difference that these 1,000 transactions result in. But if we take 2,000 transactions, that the size of the output we need to give out is not twice of 1,000 transactions, it's actually less than twice, because we omit some of the middle steps. So this can save a lot of on-chain data. Other things we can do is zero knowledge and StarkNet. Now, StarkNet itself, kind of by definition, can have zero knowledge because everyone needs to know how to run the transactions, and there is a consensus mechanism, and everything should be deterministic. So you can't have with zero knowledge, but with the recursion you can make your own zero knowledge proof at home, and on StarkNet have a contract that just verifies this zero knowledge proof and then does something with it. Some plans for the future. Maybe we want to add maybe a catch-up built-in. This is under works right now. This will make the proof expensive hashes on Cairo about 3 times cheaper, which is nice. We want to have better scheduling. Yeah, it's an interesting problem. We get it's like an online algorithm, gets jobs all the time that we need to decide who to pair up with who to make recursion proofs, and each one has a deadline. So right now we have something very basic, but we want to make it a lot better. And dynamic layout is, I'd say, one of the most interesting things we want to do. It's a bit hard to explain it, but okay. Basically, Cairo has built-ins. What does it mean? It means that although we have 16 steps in this program, it used 32 hashes and 1024 range checks or something like that. So there are different ratios between how many CPU steps I have and how many of these built-in instances I have, how many hashes instances I have. And right, each one requires different set of polynomials for a algebraic representation of the problem. So each verifier we deploy on chain only has one layout, one set of ratios between how many CPU steps we have, hashes, and that's it. And we have a few layouts to cover common cases. But what we really want to have is a single verifier that can take these ratios as parameters and then parameterize these polynomial equations. So we'll get a dynamic layout. So we can have any set of ratios we want. And it was hard to do this on Solidity. It's very hard to program that, but in Cairo, it's a lot easier. And we are starting to work on it right now. Yeah, so that's it. I think I'm out of time, but if you have questions, can feel free to ask.
Did you want to show us some code or?
Yeah. I'll share. Indeed, I can show you some code. It will be open soon. Right now, I'm working on externalizing it, but this is our code mostly. Cairo looks like a regular programming language, as you can see. Basically, we have a few phases in the verification. This is a verify star proof. You get a star proof. We have the commitment phase. We generate queries. We have decommitment phase. Somewhere we have a vector commitment, which is basically verifying the Merkle tree. It's all pretty standard code. I'd say nothing out of the ordinary. And yeah, like I said, in a few days, I think maybe next week, we should have it externalized so you can see it for yourself.